Hello, physics kids. Mr. Johansson here. We're doing mechanics number 19 today, and mechanics number 19 is all about impulse and momentum. It's kind of a big topic, but it starts out with a formula that is simply beautiful because you can access this formula in your own head so exquisitely easily. And my favorite thing is it changes how you drive. You really think about driving in terms of this formula probably from now on, and that's good. So why don't we start out with the derivation of this formula, because it's such a simple, pleasant derivation. We go to Newton's second law, F equals mass times acceleration. Consider what the value of acceleration, what the variables that give you acceleration is. Well, acceleration equals change in velocity over time. So why don't we sub that into acceleration, see what we get. All right, so m delta V, change in velocity over time. In that form, while useful, it's not incredibly useful. So let's put it in the most useful format. Multiply both sides by t, and I'll rewrite it for simplicity, but it rhymes, so it's kind of easy. Ft equals m delta v, which means force multiplied by the time that force is applied for. That's called impulse. So impulse equals force times time. What are the units of impulse going to be? What are the units here of impulse going to be? Force is in newtons, time is in seconds. So it has a unit called Newton seconds. How many seconds is the force applied for? And you can see that could be useful. M delta V. Well, we have a new idea in town. Mass times velocity. Mass times velocity. When we consider mass all by itself, that's inertia. Momentum is often called moving inertia. And I tell the story, when I was a little kid, I jumped out in front of an 18-wheeler, a huge truck, a Mech truck. I jumped right out in front of it. Do you believe that? Because it's true. I really did that. So you might ask yourself, how am I here to tell the tale? Consider mass. Whoa, the mass of that truck is huge. Is simply huge. So the inertia of that truck was vast. Why am I here then? Well, I'm here because of that. The truck was parked. The truck wasn't moving. So yeah, you can jump out in front of a non-moving truck. It has how much momentum? 0. If that truck had something other than 0 momentum, I would have been in trouble. But being massive is not enough. It has to be moving too to do something. Now, if you get hit by an 18-wheeler, a huge Mech truck, you're in trouble if it's moving. If I walk into it, I don't have that much momentum, so I wouldn't get so hurt. But when you get one of those things moving at any sort of high velocity, yeah, that could be dangerous. So let's be careful out there. This quantity is called momentum, and consider how we change momentum. Usually, it's by changing the velocity. It's rare we're changing the momentum by changing the mass. If I'm driving along, I'm probably not going to kick the passenger out. I've been told I shouldn't do that anymore. So the tiny bit of fuel I'm using up, in terms of significant figures in physics, is that making any difference at all? You'd agree, no. Now in a rocket lifting off from the launch pad, burning tons of fuel per second, well then the change in momentum most definitely is not just an increase in velocity, it's a decrease in mass. You'd have to accommodate that. But in your car, no. We're not particularly changing mass, we're seriously changing velocity. So if we're thinking of changing momentum, pretty much in all cases, if we're considering changing momentum, well, I should tell you first, mass times velocity, the unit for momentum is p. p, little p. Okay, so then we have delta p. Delta p then is going to be equal to mass times change in velocity. And again, we could change mass too, that would be fine, but that's not what usually happens. Usually it's a change in velocity. So when we put the whole formula together, Ft equals m delta v. Impulse, force times time, equals change in momentum. Okay, and usually that means a change in velocity. Examples of this. Any of you who've done anything sporting with a ball that you had to change the velocity quickly on. Consider baseball as the most typical example. You're up to bat and you hit the ball. What did the coach tell you to do? How do you hit the ball farther? When you first hit the ball, it didn't go very far. What did the coach tell you to do? Very simple rules. He said, follow through. What does that mean? Well, that means when you hit the ball, keep applying pressure. Continue as long as you can to apply pressure, to apply force to that ball, and you will knock it out of the park. Which of these things did you increase? The force was the same force all the time, but by following through, you were hitting the ball for a longer time. So you gave the ball, by following through, more impulse. And more impulse, the mass of the ball I don't suspect changed, but more impulse would give you a greater change in velocity. And that's what you're after. Pretty much any sport where you're doing anything with a ball, that's what's happening. Consider if I take a .22 long cartridge, a bullet, and put it in a rifle versus a pistol. Why does a rifle make the bullet go so much faster? It's exactly the same bullet with exactly the same gunpowder. Well, consider the two objects that we're working with. There's the barrel of the pistol. There's the barrel of the rifle. You get it? So the bullet in here has the expanded gases acting on it for a very short time. So the bullet, while it has a very large force, has a very small time that force is acting on. So the bullet doesn't get going very fast out of a pistol. But out of a rifle barrel, same amount of force, considerably larger time. So that bullet gets going seriously fast in a rifle. That's the difference between those two things. When you're driving, consider the inelegance of first-time drivers. They'll be approaching a stop sign and they will use a minimum amount of time to hit the brakes. They'll just linger too long at high velocity and then all at once. So now you have to get the car down to zero. You have to change the velocity very substantially, so you will require a huge amount of force. The reason you want to buy a used car from an older person, older people generally drive far more elegantly. So seeing a stop sign approaching, they use a moderate amount of force and a much larger amount of time, and slowly and gently stop their car. Less force on the car is less wear and tear on the car. It's an overall better car over years than if every time you come to a stop sign, you apply a vast force for a tiny amount of time. Okay, so force times time is impulse, and impulse equals change in momentum. We were talking about units for a second. Let's go back to that. Force times time equals Newton seconds, but mass times change in velocity, well, what is that? That's kilogram meters per second equals kilogram meters per second. But we're saying if Ft equals m delta v, we're saying a Newton second equals a kilogram meter per second. Now is that right? Well, to check, let's expand what a Newton is. A Newton is a kilogram meter per second squared. So if I multiply that by second, the second cancels out with the second squared, and I'm left with kilogram meters per second. Kilogram meters per second equals kilogram meters per second. So Ft equals m delta v. Pretty important formula. Impulse equals change in momentum. Let's do a problem. Let's see what a problem would look like here. You have to start suspecting that Ft equals m delta v might be the equation of choice anytime a problem has those four variables in them: force, time, mass, and a velocity change. So a 1,000 kilogram car moving at 20 meters per second uses a force of 5,000 newtons to stop. How long will it take? All right, a 1,000 car moving at 20 meters per second uses a force of 5,000 newtons to stop. How long will it take? So let's extract givens. Let's extract those givens. What do we have? M equals 1,000 kilograms. That's just a velocity. What's my change in velocity? I'm stopping. So I was moving at 20 meters per second, getting down to 0. So my delta V equals 20 meters per second. And my force equals 5,000 newtons. Looking for time. You can see this is not a hard thing, not even a little bit. The most challenging thing might be units, but it's not particularly difficult. So the formula, Ft equals m delta v. Please remember, you must solve the formula under the formula section. We never just stuff units in. We solve the formula properly here. We're looking for t. How do we get t? Well, that's pretty easy. Divide that by f. Divide that by f. The f's cancel. So t equals m delta v over f. How will we be sure we got the algebra right? As always, units. So rewrite the formula. T equals m delta v over f equals 1,000 kilograms times 20 meters per second all over 5,000. Now, instead of writing newtons, I have to check my units. So instead of writing newtons, why don't I just expand the newtons into what they are? Well, what is a newton? Kilogram meters per second squared. Kilogram cancels kilogram, meters per second cancel this meter, cancels that. So I'm left with seconds in the denominator of a denominator, which when you invert and multiply, right, we're getting rid of it here, so I'm multiplying it by seconds over 1. So here I also multiply by seconds over 1, which means my answer is going to come out in seconds, which is what I'm looking for. So some simple division then, 1,000 times 20 divided by 5,000 . What'd you get? I got that you take 4 seconds. That's what I got. 4 seconds. Okay. 20. Yep. 4 seconds. Nice, easy. So expect lots of problems like that. Expect that, man, they're easy to do. Impulse. The variable for impulse is Ft. The variable now is J. Mass times velocity, the variable is P. So those are the new variables. Of course, they're sitting in your reference tables, easy enough to look up. Check out the formula and check out some of the example problems I'll be putting on Castle Learning. Thanks for listening. This was Mechanics number 19, and it was started with a quote by Albert Einstein. Only 2 things are infinite: the universe and human stupidity. And I'm not sure about the former. Do you know what that means? Have a good one.